Hello, we're recording. So by popular demand, even though it boggles my mind that someone's actually going to watch me do problems for 2 hours and 15 minutes. I guess you're about, those of you who are here live are going to do it live. So I guess it's not too mind boggling. Okay, I am recording this whole thing. God bless you if you actually make it through 2 hours. This is like longer than a movie. My goodness. Okay, let's see how this goes. All right. So the question was ABC is equal to 0 because the vectors are linearly independent. It's the other way around. It's because ABC is equal to 0 that implies linear independence. So linear independence means that whenever you have some linear combination of v1, v2, and v3, that's a v1 plus b v2 plus c v3 equal to 0, then a, b, and c are equal to 0. And that's actually what this calculation shows. I sort of omitted that bit of work. So that's the logic is the other way around. So if having a linear combination equals 0 means that all the coefficients are equal to 0, then that implication means that the vectors are linearly independent. Okay, so yeah, it's the other way around. Okay, so therefore, yeah, and if you, oops, that's not what I wanted to have there. Therefore, actually, if you get anything out of this course, if you kind of get if you really understand what linear independence is, which I know after taking 129A, I think a lot of people don't, just because it's sort of so calculational. But if you get that's something. That's like a non-zero achievement right there, and super useful. All right, so therefore that blah 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 is a basis for W because it spans by definition. The dimension of W equals 3. Well, actually, all you need is a basis for W. So W is the set of all linear combinations of that exactly of v1, v2, v3, and they are all different. So W contains 7 cubed vectors, which happens to be equal to 343. Is that right? Yeah, 343. And the 7 comes from the fact that the coordinates are taking mod 7, or that you're working over the field F7. All right, and by the way, the 5 basically plays no. I mean, everything below here is just all junk. And the 5 actually plays no role in this problem. So, questions so far? And let me save this before I forget. This is 2020, May 13th. Okay. All right, so questions so far. So if we do row reduction, what should we see? So if you do row reduction and after REF, if all of the columns are pivots. So the original vectors are linearly independent if and only if, exactly when, all the columns are pivots. So if you do this by row reduction, I guess I might as well mark this. Okay, maybe this is somehow worth watching. After row reduction, we see that if so the alternative way to do this, this is the way everybody would actually do this probably, is that all pivots after REF. That's the same thing as saying linear independence. Okay, yeah, great. And John B asks the question: how did I get 7 cubed? Well, let me write that in. So 7 cubed equals 343 vectors. You get 7 choices for each of the coordinates of v1, each of the coefficients of v1, v2, and v3. Right. So basis. So having a basis means exactly that. Yeah. What does it mean to have a basis? Then that's actually equivalent to saying that every time you choose a different coordinate for v1, v2, and v3, you get a different vector. That's what having a basis means. So yeah. So this is sort of, I mean, and this is sort of a thing. It's interesting. You can't sort of do this same kind of calculate. You know, if I knew we were going to record, I would have paid more attention to my appearance. Hello, YouTube. Maybe a little unshaven or something. Okay, right, yeah. So that's the whole, that you sort of can't see this because you can't, because the answer is always infinity in 129A. But suddenly when we have a finite field, you can actually sort of see that, well, oh yeah, we have 7 choices for each one. So there's 7 cubed vectors. All right, so that was actually turned out to be kind of an informative problem. Good so far? All right. Next. I forget what order I wrote these. I think these are actually kind of, well, these are in random order. Okay, so number 2. So recall the various forms of the division theorem for a ring R. I'll say that when we divide A by some non-zero D, we get blah. A plus equals QD plus R for some Q and R such that R is in some sense smaller than D. Compare the statement of the division ring for the following rings R. The division theorem, sorry, for the following rings R. Part A. For R, when R is the integers, when R equals Z, in what sense is R smaller than D? Well, there are 2 possible answers here. So A, answer 1. We could have that 0 is less than or equal to R is less than D. So that's the sort of standard division theorem. Or we could have answer 2. The absolute value of R is less than or equal to the absolute value of D over 2. This is the signed division theorem. This is, we haven't forgotten. So this is to remind you that we have not forgotten chapter 3. It's still there. It's still going to be part of the exam, and it's important. And I still want you to understand this stuff. So this is an important part of chapter 3. All right, or maybe this is chapter 2. Anyway, I thought I saw. Did somebody else have a question on the chat that I did not answer, or there's Zoom is like bothering me about something. What is that? Hello, I'm your DocuSign bot. Okay. Oh, oops. Okay. Sorry, I should. Let me pause. Let me pause the recording for just. And we're back, YouTube. Hello. All right. So now, okay. So that's. Okay. Right. Thanks, Kyle. Sorry about that. I hope nobody else is out there waiting to find the link, but I guess now they can watch it on YouTube. Thanks to somebody asking me to record this. Okay, if you're really going to watch this, okay. I guess if you're willing to sit through 2.25 hours of this live, you might might be willing to sit through slightly less of that if you hit the fast forward. What's really great about YouTube is the 10-second skip button. I live for the 10-second skip. All right. All right. Speaking of things that are skipping, there we go. All right. So does everybody see does everybody go the 2 answers to part 2, to number 2, part A? So number 2, part B. So when F is if F is a field, then R is the ring of polynomials, the coefficients in F. And in what sense is R smaller than D? Well, what we need is when the degree of R of X is strictly less than the degree of D of X. And actually, it's sort of it's worth noting that it's important in so that in answer number 1 for A and for the answer for B, there's only one answer, is strictly less than. Yeah, so not less than or equal to. So because if you remember, the thing that makes the Euclidean algorithm work in either the integer form or the polynomial form is that whatever this size of your thing is, your quantity is, the problem is it gets strictly smaller. If the quantity got only sort of loosely smaller, then it could stay like 5, 5, 5, 5, 5, 3, 5, 5, 5 all the time, and then the algorithm would never finish, so not so useful. That's sort of not a desirable quality in an algorithm. Right. So yes, that's right. So this. So let me see if I can scoop some text here. So right. This is. Oops, that's not what I wanted. Let's try. Maybe this will work. So this. So this thing here has to be less than. That didn't work at all. Let's try this. Okay. So yeah. So as Ryusei is asking, that symbol right there has to be strictly less than, not less than or equal to sign, and it's less than or equal to for the sign division theorem, and less than for the standard division theorem and for the polynomial division theorem, that you have strictly less than, and for the sign division theorem, all you can get to is less than or equals to, because there's this ambiguity of a half, for better or worse. So Ryusei, did I answer your question? Yeah. So it's weird that, I mean, this is sort of, I mean, usually algebra classes aren't so fussy about like inequalities, but this is one of the key points. I think maybe even the only key point in this class where you have to be really fussy about less than or less than equal to. And, usually, well, I guess, the point is that the size of your problem gets smaller, and strictly smaller, and that's true here. And actually, even here, the size of your problem is getting strictly smaller, because all you really need is that the absolute value of r is strictly less than the absolute value of d. But it's sort of less than or equal to the absolute value of d over 2 is even better. It's like not only is the remainder smaller than the divisor, it's less than half it's at most half the size of the divisor. So it's sort of quantifiably exponentially smaller. Anyway, so any other questions about problem 2? So we good on problem 2? Okay, now on to problem 3. Oh yeah, problem 3 is a fill in the blank. So I guess, yeah, you can sort of see, I mean, so there will be something like these on, there might be have a slightly different flavor, but I hope you can sort of see that the first 4 problems here are all sort of recite the theorem, do you understand the theorem? And so that they might be, there probably won't be any problems like we have in number 4 here, which is just like state the theorem. Like, well, I hope you all realize that cosets are important to this. And so that you will all write down the definition of coset, especially since it's right here on your page of notes. But something like that, something testing your understanding of terms and your understanding of what various theorems say. Some stuff like that will be on Saturday. I mean, it has to be a little bit different because this is an open. This exam that I gave last year was a closed notes exam, so I could just have some things where I just say, well, just recite this, and this year's open notes, so there won't be anything like that, but there'd be maybe something slightly more involved. Friday. Oh, Friday. Yes. Oh my God. Terrible. Yes, our exam is on Friday at 9:45. I have a different exam on Saturday. I'm sort of in charge of a different exam on Saturday that I've been thinking about all day. My bad. So, okay. Hello, this is Math 127. I'm saying that for myself mostly because I seem to have forgotten. This is Math 127, Applied Industrial Algebra. Our exam is from 9:45 until noon on Friday. There. Okay. Right. Let's see. So are we good? Everybody good to go on to number 3? Okay, I think I will actually probably pause for a little bit less time than usual. So how do you construct the field of order 2 to the e? So the way you do this is you always have to start off with polynomials. How do you construct a field of order 2 to the e? You always start off with polynomials with coefficients mod 2. That's what f2 bracket x is. And you mod out, and you're going to kill some particular polynomial m of x. So the first thing to remember is that every finite field of order 2 to the q 2 to the e is you get by taking polynomials with coefficients mod 2 and by killing a single polynomial. And what is important to know about that polynomial? It's important to know that polynomial is irreducible polynomial. And what is the degree of that polynomial? Well, so we see here we're trying to make a field of order 2 to the e, and so that polynomial has to have degree e. So for example, so this is actually not, now I'm just going to explain things, and this is not part of the answer per se, but so for example, e.g. to construct the field of order 32, which is 2 to the 5, we start with f2 bracket x polynomials with the coefficients mod 2, and take a quotient, mod out by the ideal generated by, kill, and irreducible polynomial m of x of degree 5. Right, and you may be wondering, I started to circle this, but you may be wondering where that 2 came from. In case you're wondering where that 2 came from, that 2 comes from the fact that we're ending up with a field of order 2 to the e. Ugh, not quite big enough there. So yeah, the 2, the reason we have coefficients mod 2 is that we're taking is that we're looking to construct a field of order 2 to the e. Remember, any field has order p to the something for some prime p. And so where does the e come at the end? I hope you see, I hope you realize, but just in case, I will indicate that e comes from the fact that it's 2 to the e. I just made that totally unreadable. Huh? Like, let me try that again. Did all that effort, and then I made something that is very hard to read. Let's try that again, shall we? So the point is that we have q equals 2 to the e. There we go. Nice and big. And so that 2 is the reason why we were taking coefficients mod 2. And I see your chat question, and that e is why we're taking why we're taking a polynomial degree e. Okay, and now let me go back. Yes, so again, remember F32. So remember, one of the things that, and it's very, I myself made this mistake for a very long time, sort of don't tell anybody else, but past the time I got my PhD, when I supposedly sort of knew all about this. Remember, so it's always the confusing part. F32, for example, is not the same as Z mod 32. For example, Z mod 32 is not a field, because 8 times 4 is 0 mod 32, and neither 8 nor 4 is 8 is not 0 mod 32, and 4 is not 0 mod 32, and so Z mod 32 has 0 divisors, and F32 does not. So F32 you get by the field of order 32, you get in this sort of strange, complicated manner. So all those things about, remember how we, just for example, it's like the wrong shade of red. So no, that's right. I'm just diluted. So for example, F16 is you can construct the field of order 16 by taking coefficients, polynomials with coefficients, and the field of order 2, mod 2, and modding out by x to the 4 plus x plus 1, which happens to be an irreducible polynomial of degree 4. So here's another example. So I know, very confusing that you have to make the field of order 16 in this complicated way instead of like, oh well, why can't we just do mod 16? Well, you can't do mod 16 because it's not a field, but this is, and the fact that it's useful is weird, but it is. Remember that, because that's how we make create BCH codes. All right, so There's not only an answer to the problem, but some explanation. So any questions about that? So is problem 3 good? Yeah, that's a deep. You say the fact that you're asking that question, it means that actually kind of indicates they understand it, because like once you sort of understand that that is the deal, that it's not just integers mod 32, is that you have to do this strange thing. Well, that's life. I don't know. Don't blame me. Blame the universe. It's the way the universe is set up. What do I know? All right. So the next problem is very straightforward. This is meant to just be a recitation of a definition. So let G be a group, let H be a subgroup of G, and let A be an element of G. Define the left multiplicative coset AH, and this is just a straight up definition. A capital H is equal to the set of all things in the form A little h, where little h is an element of big H. That's all there is. So this is a definition from chapter 10. See chapter 10 definitions, and see also problem set 11, because that's the one place where you have the problems from chapter 10. So so how are we good? Are we good on problem 4? So we good on problem 4? And so, I cannot recommend more strongly, maybe if you could somehow speed this up for like watching me, if you really are watching this, but instead of watching me for 2.25 hours, I would do a problem set or two. That would be much more, or at least take a look at the problems, make sure you can do it. Because the exam is going to be taken really just directly off the problem sets. As much, I think I've been doing that pretty consistently. I hope that's my intent anyway. At least that's what I try. I mean, doesn't always work out that way, but definitely, yeah, I'm going to try to take things directly off the problem sets. All right. Next. So that was problem number 4. Oh, problem number 5. Yeah. Oop. Why is it doing that? Okay. So problem number 5. So let A be a matrix with entries in F5 such that the reduced row echelon form of A is blah, this thing 1 2 0 1 4 0 0 1 3 2, and then a row of zeros. Find a basis for the null space of A and show your work. So I think probably the way to go about this is to note that these columns 1 and 3 are pivot columns, and which means that the other variables x2, x4, x5 are the free variables. I thought I saw, did somebody have a question in the chat there? Oh, there was a problem about transversals on PS11s. I did not, okay, so yes. So I will, we can talk about, I'll do an example of that. I think I'll just repeat something from class. So John B, can you, I think we should finish up, at least at this pace. I think we should finish the exam, going through the answers for the exam before 5 o'clock. So when we have extra time, can you bring that up again? Yeah. Okay. So I want to do that, but I'll just forget. But so if you can just remind me by the time we get to the end, that'd be great. Okay. Right. Oh, find a basis for the null space of A. Well, so if you remember how this goes, what you want to do is you want to write this out as equations. So now basically here's the answer. Now you just want to write out what that means in terms of equations. So what we have that x1 is equal to minus 2x2. That's one of the free variables. Minus 1x4 minus 4x5. So that and remember, so this is the idea is that this represents everything over on the left-hand side of an equation, and we push them all to the right-hand side. And then x3 is the other pivot variable. So x3 is equal to minus 3x4 minus 2x5. And now our free variables are x2 and x4 and x5. Where's my little green dot at? There we go. And I know that I certainly can never keep this straight if I don't sort of put in these kind of silly equations. And now the way that we read off a basis for the null space of A is that we just if we line everything up carefully, then we can just read a basis for the null space of A, but just from this display here. So that's going to the basis vectors are in dimension 5. They're -2, 1, 0, 0, 0, comma, -1, 0, -3, 1, 0, comma, -4, 0, -2, 0, 1. And okay, so I will accept this answer. And I guess in many ways it's safer, but just in case you're wondering, this is 3, 1, 0, 0, 0, comma, 4, 0, 2, 1, 0, and the last vector is 1, 0, 3, 0, 1, 1, 0, 3, 0, 1. And remember, these are equal because all coefficients are mod 5. And why are they mod 5? Oh yeah, so this over here says that everything we're doing in this problem is mod 5. Okay, so gee, I guess I better pull out for this. Oh, well, look how much room I had. Oh well. Is there some middle ground here? There. All right, so okay, so everybody good for that? Problem 5? Okay. All right, so let's get back out to page width. So next, problem 6. Oh yeah, so let E be the field of order 32. And here we don't need to think about, I mean, it is constructed by taking F2 bracket X and modding out by some irreducible polynomial of degree 5. We don't need to know that. All we need to know here is that we have this thing alpha, which is a primitive root of unity, and alpha has order 31, because 31 equals 30. What is it? Equals 32 minus 1. That's where that came from, right? I mean, you always want, inevitably, if you're a thoughtful person, you say, like, where did that 31 come from again? And it came from the fact that we have a field of order 32. And but remember, the multiplicative group has all the non-zero elements, and so we throw out 0, and so that is the order of our primitive element. So the exponents are all calculated mod 32. 31. All right, I gotta get my head in the game here. I'm being recorded again, so I have to think harder, not to embarrass myself. Okay, yeah, so alpha be a primitive root of unity, and let C be the corresponding BCH code of design distance delta equals 5. So where did that go? That was weird. All right, so when we have, so delta equals 5, what does that mean? That means we're gonna want M1, we're gonna have to account for M1, M2, M3, and M4 somehow. Right, because what we need is that we need why is that? It's because what we want is that we want G of alpha and G of alpha squared and G of alpha cubed and G of alpha to the fourth all equal to 0. And somehow because all those things are true, because all those powers of alpha are roots of our generator polynomial G, that means somehow that the minimum distance of G is at least 5. For whatever reason, that's the truth. That's a fact. So find the generating polynomial G of C as a product of minimal polynomials M sub I of X. And so what we have to do is we have to compute orbits. So for A, we're gonna have to compute orbits of 1, 2, 3, and 4. Or I guess of alpha to the 1, 2, 3, and 4. And you know what? I guess I will just to be fussy. I will actually write it out with the alphas because it doesn't take that long. Alpha, but if you want to just write in 1, 2, 4, 8, and so on, that's fine with me. Alpha squared, alpha to the fourth, alpha to the eighth. So remember, this is orbits. The orbits that we compute are the orbits under the Frobenius automorphism, which is a fancy word for squaring, and then we get alpha to the 32. And remember, alpha exponents are mod 31, and so alpha to the 32 is equal to alpha to the 1, and so we're done. And so remember, we're sort of invisibly circling back here. So that's the orbit of alpha to the 1, orbit number 1. But that's also equal to, as you see, because alpha squared and alpha to the fourth also appear here. This is equal to orbit number 2, and also equal to orbit number 4. And so the only other thing we need to compute here is orbit number 3, which is alpha cubed, alpha to the 6th, alpha to 12, alpha to the 24, alpha, and square that, alpha to the 48. 48 mod 31, finally I'm going to get that right, is alpha to the 15. And alpha to the 15 squared is alpha to the 30. Let me try that again. 17. There we go. There we go. And alpha, as I was saying before, I so rudely interrupted myself. 48 mod 31 is 17. There we go. And alpha to the 17 squared is alpha to the 34. Mod 31 is alpha cubed. And so indeed, we circle back. I guess I should sort of. So here, what happened in the previous example is that 32 equals 1 mod 31. And over here, we have that 34 equals 3 mod 31. And so that's why we circle back. Right. And then we're done. Okay, so then we see that I guess you're not actually asked for this. So what you're actually asked, let me do actually the minimum of what you're actually asked. What you're actually asked to say is that g of x is equal to m1 of x times m3 of x. And then the degree, and we see the degree of m1 is equal to the degree of m3 equals 5, which we'll need for the next part. So the degree of g equals 10. So that's the end of part A. I guess yeah, while I'm waiting to see if How did I get 10? Oh, I guess I was going to say, well, it's from stuff I skipped that you don't have to write down, but let me do it anyway. So m1 of x is equal to, what is actually the minimal polynomial of alpha? It's x minus alpha times x minus alpha squared times x minus alpha to the fourth times x minus alpha to the eighth times x minus alpha to the 16th. All right, so that's what m1 of x is. So that has degree 5. So m1 of x has degree 5. And in a very similar way, m3 of x has degree 5. Actually, and you can tell that you can without having to write this out, you can tell that m1 of x and m3 of x have degree 5 because, well, why was it that m1 of x has degree 5? It's because there are 5 things in this Frobenius orbit. Why does m3 have degree 5? It's because there are 5 things in this Frobenius orbit. And so, yeah, so remember, degrees add. So if you have the product of two polynomials of degree 5, you get a polynomial of degree 10. And so the degree of G is 10. So Rudra, does that make sense where that degree of 10 comes from? All right, great. It's a good review. Yeah, so the degree of our G is 10. And what's the, and remember, and so then the only thing left to do is to figure out the degree of part B, the dimension of our code. But remember, the dimension of our code is the length of our code, which is 31, minus the degree of the generated polynomial. So this is sort of 31 is the order. I'm just going to ignore that phone. The order of alpha, and 10 is the degree of G. And so the dimension of your code you obtain by starting with the order of alpha and subtracting the degree of G, and now we get 21. So so there we go. All right. So that's part B. So does everybody get, what problem are we on? This is problem 6. So does everybody go to problem 6? Whoa, that doesn't help. That's closer. What was the, Ruse, what do you mean by, the minimum distance again? Delta was 5. Right, so remember, delta is 5. And that's why we wanted the minimal polynomials 1 through 4. But really, the minimal polynomials 1, 2, and 4 are all the same. So we really just need minimal polynomial 1 and 3. That's hard to say, minimal polynomial. What's that TikTok thing about, like, Cadillac? Oh, I don't know. My wife and kid watch this all the time. Invincible something Cadillac. Okay, never mind. Thank you for indulging my old man moment. All right, so you say, did I answer your question before I started going off about TikTok and this guy who talks about something Cadillac? Okay. Yeah, so that's the minimum distance. Yeah, so well, we don't know. So so we know that the minimum distance is at least 5, but to find the actual distance, we don't know that the actual distance is more than 5, but it could be. So it could be that somehow you put this thing together and then it just happens that like all your words happen to have at least length at least 8. Uh, and that's actually you just can't tell. You just actually have to write down all the words. I mean, you have to it's dimension 21, so you'd have to just write down all 2 to the 21 words. And actually, I think actually, some enterprising person. I think the second time I've taught this class. This is the third time now. So last year, somebody I said this, like, well, you just have to check all the words, and somebody very reasonably said, like, that can't possibly be true. And then he went and he looked it up, and apparently, yes, you have to check all that. Like, there's not a better known algorithm in general than checking all the words. Yeah, but but as far as we can, I think it's probably true that. I believe it's true in this case that the minimum distance is the actual minimum distance, the design minimum distance. But all we know is that we don't obviously have a better minimum distance than designed. So yeah, okay, great. Any other questions? Yeah, I guess the official statement, I should say, is that I don't know if you guys have heard about this class of problems called NP problems, which has some technical definition, but I always think NP stands for not possible. There's the problems of type P, which are basically possible. I mean, even those problems aren't really possible, but there's the possible problems and the not possible problems. And the problem of finding the minimum distance, given a generating set for a basis for a code, finding its minimum distance, that's actually one of the not possible problems, because you can sort of encode, you can sort of disguise, if you could solve that problem, you can solve one of the sort of known not possible problems. At least we think they're not possible. Anyway, that's a total tangent. And you want to just like take this exam. So I understand. Let me go on. Let me focus on the exam. Okay, so problem 7. Oh no, did I really sign this? Oh God, I can't believe I'm going to do this on tape. All right, here goes. So consider A equals 8x to the 4th plus x cubed plus x plus 1, and B equals x squared plus x in F2 bracket x. Use the Euclidean algorithm to find the GCD of A and B. Show all your work. Oh God, who volunteered for this? All right, so the way you do this with polynomials, since I'm not going to be required to sort of make sense of this all and keep track of this all, is I want to keep dividing, keep doing repeated division with remainder, and then remember between each time. That didn't work at all. Can I draw the number 3s? Oh, there we go. So x to the 4th plus x cubed plus x plus 1. All right. So what you do each time is that remember that is that the old. Oops. I want this to be blue. What's going to happen when we do this at each step is the old divisor becomes the old remainder becomes a new divisor. And the old divisor, everybody gets sort of promoted up one rank. The old divisor becomes the new thing being divided into. Which I never remember the name of that. The dividend, something like that. It moves in here. Okay, so let's go ahead and do this. So x squared goes into x to the 4th. Oops, x squared. Actually, I should be a little more careful. Let me be a little bit more careful here, even though I sort of can get away without doing it. So I want to move this x plus 1 over a bit, because when you do long division like this, you always want to leave a space for the squared term. So all right, so x squared goes into x to the 4th x squared times. So we pick up an x squared over here. And so x squared times x squared plus x is equal to x to the 4th plus x cubed. Look at that. And we get a remainder of x plus 1. Oh, thank God. X plus 1 is is degree less than 2. So this is the degree of that thing is strictly less than the degree of the divisor, x squared plus x. And so we stop. And so now, that, like I said, the old divisor becomes the new thing being divided into, and the old remainder becomes a new divisor. So let me indicate that with green pen. All right, so now, then we do this again. Let's see, so x plus 1 goes into x squared plus x. Oh, it just happens to go in exactly x times x squared plus x, as if this was sort of rigged to work out. So, oh, thank God. I wasn't in too cruel a mood when I wrote this. So oops, I keep forgetting to make this blue. So the last non-zero remainder is x plus 1, which means that the GCD of a of x and b of x is equal to x plus 1. Whew. All right, so that was number 7. So everybody good? So is everybody good with problem 7? Is everybody good with problem number 7? Now this is going to bother me like all afternoon if I don't find out. Does anyone remember that thing on TikTok that's interior something Cadillac something something? I remember the first word now is interior. I'll look it up later. All right. So anyway, so that's done. Perhaps you are now saying yes. Please move on. Okay. Problem number 8. Yes, that's it. Interior crocodile alligator. There we go. Yes, something like that. Thank you, Kaushal. All right, so let's go on to number 8. So right, so in F2 bracket X, we have the following facts, blah, blah, blah. So then, and actually, if you compare what was going on in the previous problem, what we have here is that the process we had in the previous problem of using the Euclidean algorithm to find the GCD of 2 polynomials, that's actually the same. This is sort of the output of that process. So what I've sort of done here is I've taken this whole problem, sort of, taking you to finding the GCD of 2 polynomials, and then sort of using that to find inverses, for example, in a finite field. And this is I split in 2 parts, and sort of they're done separately. But it's really, conceptually, you might think of this as actually all part of one big thing. Anyway, so let's go ahead and do the problem. So now we're given these facts, and we're going to find the multiplicative inverse of alpha cubed plus alpha squared plus 1. And so what happens, so let's call this thing beta. That's an element of F32. And the corresponding polynomial is b of x. And this is going to be our m of x. M of x, there we go. So what we have here, and I'll put in an extra step actually. So the first equation actually says m of x is equal to x squared plus x plus 1 times b of x with a remainder of x squared plus x. And actually, so this first step is not necessary. I mean, all I'm doing, I'm just copying over the first equation, so I didn't really need to do that. However, if you've made the error in the past, or if you want to avoid the error, where you confuse b of x and the thing and its the sort of quotient that you get here, it's not a bad idea to sort of rewrite that first equation. Anyway, for what it's worth, that first equation becomes, so when you do your Euclidean rewriting, you put everything over the other side, and you have m of x, well, minus the thing that was on the right hand side, but thankfully everything is mod 2, and so minus is equal to plus. M of x minus x squared plus x plus 1 times b of x. Okay, so we get that, and that's star. So that's just rewriting star. There we go. And now, if I now rewrite double star, what are the chances? Oh, actually, well, let's make like a star. If I rewrite double star, we see that 1 is equal to, oh, right, I guess I should label this as b of x. 1 is equal to b of x minus, oh yeah, because minus is the same as plus, remember? Plus, because it's the same as minus, x times x squared plus x. And now you sort of want to be able to, so that's just rewriting double star. So everybody's good so far? Okay. And so now, and so the one other, so I think a lot of people got this on exam 2, but just, if you made a mistake, the one confusion I already talked about. Here's the second confusion that people make. Then where the next step comes from is you kind of teleport, you substitute this term for this term over here, because that can be expressed in terms of b and m. And we want everything in the end to be expressed in terms of b and m's. So 1 is equal to b of x plus x times quantity m of x plus x squared plus x plus 1 b of x. And so this is equal, and if we rearrange this, we get x m of x, that term doesn't matter, plus, and remember, as they said in your non-abstract algebra class, in your sort of non-abstract, non-applied class, there's like an invisible 1 here, right? There's always a little invisible 1 at the beginning of every term like that. And so when we combine, when we gather all of the b terms, what we get is parens x times x squared plus x plus 1, all that plus 1. There's an extra 1 coming from over here, and the invisible 1 ends up being over there. And so we get that times b of x. And so mod m of x, which is sort of really what the whole point was. Remember, the whole point was we're working sort of mod alpha to the 5th plus alpha squared plus 1. That's what this phrase here means. That alpha is over root of that. Mod m of x, we get, well, the m of x stuff goes away, and we get x, oops, not x, but now alpha, because when you take x mod alpha, when you take x mod m, you abbreviate that as alpha cubed plus alpha squared plus alpha plus 1 times beta. And so beta inverse equals alpha cubed plus alpha squared plus alpha plus 1. That's the final answer. Whew. That one takes a little work there. That's a little bit too big there. Okay, so any questions about that now? Good. Oops. Sorry, I meant to say that, send that to everybody. That's problem 8. 5 more to go. Okay, next. Problem 9. So problem 9. Let's see. So let C be the binary linear code. Oh, actually, I think in some previous problem I said, well, if you did it by RREF, well, somebody's asking what happens if you do this by RREF, and so I'm going to do that. So A, find the dimension of C, justify your answer. To start part A, our code C is equal to the column space of G. That is, oh yeah, it says right there, C is span by the columns of G. So that if I then do RREF, or even just reduce echelon form, I hope you can see that, and I would take it as like, well, this is pretty clear that I can take this entry here, and this entry here, and this entry here, and wipe out everything underneath them. And so what we get is 1, 0, 0, and then some more zeros, and then 1, 0, and then some more zeros, and then 1, and then some zeros. So Ryusei, you're asking what happens if you get linear independence. What do you get for your reduced row echelon form? Well, you get basically an identity matrix sitting on top of a bunch of zeros, and so this so this shows that the columns are linearly independent, as I said over there. So the dimension of script C is 3. Okay, and that is sufficient justification. So yeah, there's an alternate way of proving linear independence. You probably like that one, especially since this one here you don't really do any work with for the reduced row echelon form. I guess that was actually true in the other one, but is everybody good with that so far? Oh yeah, how did you make everything disappear with the reduced row echelon form? So well, the thing is, yeah, let me do that in a little bit slower motion. So yeah, because to be honest, I would accept this. So 101, let's see. So let me do this in slightly slower motion. So we start off with alternating ones and zeros. 0, 1, 0, 1, 0, 1, and then 0, 1, 1, 0, 0, 1, 1. And then 4 ones bottom. Okay, so and so the first step here is going to be we subtract R1 from R3, R5, and R7. And I get okay. Let me be honest here. I'm going to type out sort of formally what you do. But to be honest here, I see that row number 1 over here, which is 1 and a bunch of zeros, and I know that no matter what I do, I can just sort of use that 1 over here to wipe out everything underneath it without affecting anything that in the other column. So as soon as I see that 1, 0, 0, that's like that's good. I can wipe everybody else out. But whether that sort of formally makes sense or not, I hope you see that if I subtract row 1 from rows 3, 5, and 7, I get 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. Look at that, actually. Yeah, so that wasn't so bad. Yeah, okay, so that makes sense. So John B asked, does it have to be the column space or does it have to be the basis of the null space to consider the dimension? It depends on your problem. And you have to sort of, and part of this problem is is testing that you understand the vocabulary of when you use the column space and when you give the null space. Um, so uh, so when you see the words generator matrix, that means you're using the column space. And then this isn't this problem, but that we could easily do. That could easily be on Friday's final. If we start with the parity check matrix, then your code C is the null space. Say parity check matrix H is the null space of H. Yeah, so the keywords to look for are for generator matrix. You use the column space, as it says so right down here. In fact, this is sort of reminding you of that fact down here. And if you start with what's called, if the problem says we start with a parity check matrix, then we take the null space. So does that make sense? Okay. All right, so that was part A. And maybe in more detail than necessary, but not in a bad way. Now part B. For part B, this says find a non-zero code word in C that is not one of the columns of G. C is the span of the columns of G. Actually, I guess I better write out those columns. 1 0 1 0 1 0 1, comma 0 1 1 0 0 1 1, and then 3 zeros 1 1 1 1. So let's call this V1, V2, V3. And so remember, so C is the span of those things, which is the set of all linear combinations of V1, V2, V3. So if we want to find a vector that's not a vector in your code that's not one of those columns, let's take V1 plus V2, which is 1 0 1 0 1 0 1. Oops. 1 plus, my daughter's sort of running around the background here. 0 0 1 1 0 0 1 1. Oh, it's a very messy 0 here. 0 1 1 0 0 1 1. That didn't really help. Okay. Anyway, so when you add those two things together, you get 1 1 0 0 1 1 0. Oh, that's not unpleasant. So that is a code word that is not equal to one of the original columns. Yeah, okay, so what is that really testing? This is really testing, what is it really about? This is about the idea of the ideas of basis and coordinates and span. Yeah, so basis. The idea of a basis for a linear code. And there are 2 to 3. So there are 2 to 3, two cubed possible code words. Um, huh. Well, yeah. Actually, now that, for a non-zero code word. So yes, I did eliminate 0. So there's let's see. So there are 8 possible code words. There are 8 possible code words. You can't have 0. You can't have your 3 basis. Can't have your 3 basis vectors. And so there are 4 possible answers. There are 3 other possible answers. And I guess they're going to be V1 plus V3, V2 plus V3, and V1 plus V2 plus V3, as it happens. All right, so let me, I think that's the name of that tune. So let me stop there and ask if anybody. So whatever spans the basis has a linear combination general. John B, I'm not sure I understand your question. Can you state that in a different way, or type out or say it out loud if you're willing to be on YouTube?
So you wrote out the span and then you showed it has a linear combination. So that's what my question is.
That is the definition of the span. The span of 3 vectors is the set of all linear combinations of those 3 vectors. So it's the definition. I know, it's like the most annoying thing to say, right? Like why is this equal to that? That's the definition of span.
Oh, okay.
And so, which is like the most annoying thing to say, right? Like it's by definition, because it sort of somehow makes it sound like, well, this is not hard, but it is hard because definitions are hard, and it's very strange. It's just so I mean, I'm so used to it, having sort of thought like this for about I guess 30 years now. I've been sort of, for about 30 years now, I've been paid money to think like this. So it's hard to remember like what it's like not to think. But I even remember taking physics, and in physics, like it's a very different philosophy, right? Because in physics there aren't definitions, because you have to because instead of definitions, you believe in this thing called reality, which I have very little. Well, whatever, man. You can have your reality. I prefer definitions. I mean, but I don't. And like the one reason I never got very far in physics is that I would always sort of get to some point like, well, what is the definition of angular momentum, or like what is the definition of force? But there's no definition. There's just this is like what it is. You push the force. That's a law. Let's see. So anyway, sorry. So but this is really by definition. So I mean, in math, it's very different. You don't rely on reality. There's no reality. There are only definitions. And that's sort of what makes it lucrative, is that you do things that you wouldn't or sort of be able to do just by restricting reality. All right, Nat has a less philosophical question. It would not be an answer if we chose a multiple of one of these vectors. It's a binary linear code. It's a binary linear code, which means the coefficients are all mod 2. So the only coefficients to pick are 0 and 1. So right, there are no other multiples of those vectors other than the basis vectors themselves. So yes, that's correct. Yes. So yeah. Those are the basis vectors are the only non-zero basis multiples of themselves. So because binary. Oh, I'm not quite used to that happening here. Let me remind you that binary always means it doesn't mean in this course binary codes don't mean just like they're just not that just they're zeros and ones. The coefficients are everything is done mod 2. All right, good question. Okay, any other questions? 4 more problems to go. We'll have a little bit of time after this to talk about other stuff. Not a huge amount, but a little. Okay, so orders. So let F16 be F2 bracket A, where where alpha, so F2 bracket alpha, where alpha is a root of x to the fourth plus x plus 1, which means that alpha to the fourth plus alpha plus 1 equals 0, and we'll elaborate on that in a minute. So that's sort of the governing law of this ring. And so let beta equal alpha squared plus alpha. And suppose we're given that the order of beta is less than or equal to 5. Find the order of beta by calculating powers of beta and using the given information, show all your work. All right, so what the method for doing part A is that we're going to calculate beta raised to the power of 1, 2, 3, 4. First period. First one of those powers that's equal to 1 gives the order of beta, and if none of those are equal to 1, we're given that the order of beta is at most 5, so then the order will be 5. So before we do, I do want to emphasize here that before we do any calculation, all you have to do is calculate beta to the 1, beta squared, beta cubed, beta to the fourth, and see if any of those are equal to 1. If none of them are equal to 1, then we since we know that the order is going to be at most 5, we just say, oh, beta has to have order 5. But well, actually, we'll see what happens. All right, so does that make sense as a beginning for this problem? So you don't have to sit there and calculate powers of beta forever. You just have to go up to 5 because we're given, or you just have to go up to 4 because we're given the order is at most 5. So does that make sense? Again, that's the definition of order. All right, that's actually probably more important. That idea is more important. I know that idea is more important than the details of the problem, but we'll do the details of the problem. Now, for the details of the problem, the calculational part, which, okay, that is actually also important. So alpha, we know that alpha to the fourth is equal to alpha plus 1, which means that alpha to the fifth is equal to alpha squared plus alpha, and alpha to the sixth is equal to alpha cubed plus alpha squared. All right, so and we're going to use it as we compute powers of beta. So beta equals beta to the 1 is beta is alpha squared plus alpha. That's not equal to 1 because that's already reduced. Beta squared is equal to it's equal to alpha squared plus 2 times alpha squared plus alpha, which is 0. Remember that middle term is always 0, and then alpha times alpha is alpha squared. Right, and just in case you were like, why is that? Oh my gosh, why is that middle term equal to 0? That's equal to 2 times alpha squared alpha, right? You remember because of FOIL, but still, so that's what we get from FOIL, except that everything is mod 2 in this ring. Right, in the field of order 16, everything is mod 2, so that 2 alpha squared times alpha is actually 0. And so we get alpha to the fourth plus alpha squared, but we know that alpha to the fourth is equal to alpha plus 1, and so this is equal to alpha squared plus alpha plus 1. All right, so does everybody go with alpha squared? Sorry, with beta squared. Good. Okay, so now let's do beta cubed. So to calculate beta cubed, you don't want to sit there and cube that thing out. Beta cubed is equal to beta times beta squared, beta squared, which is equal to alpha squared plus alpha times alpha squared plus alpha plus 1. Oh, goodness. Um, geez. Alpha squared plus alpha plus 1. I mean, okay, I'll be honest. I can sort of do this in my head, but actually, it's probably better to show a more durable way of doing this. So you can actually just sort of do this out in terms of, right? It depends on how much money is on the line, right? Like if I have $1 million on the line, if somebody told me I'm going to give you $1 million if you get this correct, I would do this. So I guess in terms of a final exam, it's not such a bad idea to do this out. All right, so that's alpha squared plus alpha plus 1 times alpha squared plus alpha. And then thankfully, these things cancel out, right, because there's 2 of them. And we're left with alpha to the 4th plus alpha. So this is alpha to the 4th plus alpha, which is equal to, well, alpha to the 4th is alpha plus 1 plus alpha. Oh, hey, that's 1. Look at that. What are the chances of that, huh? So the order of beta is 3, because the order of an element in a multiplicative group is the number of times that you have to multiply that element times itself to get 1. So what happened to the whole page? No, it's too small. Okay, so is everybody good with part A so far? Okay, so now part B. Part B is shorter, but maybe more theory-ish. Okay, so now part B. Part B, oops, and this is like too small to read. Part B, well, part B says that every finite field of order Q has we know that these are the 5 facts finite fields. We know that every finite field of order Q has a primitive element which has order Q minus 1. Here, Q equals 16, so there exists a primitive element of order 15. Yeah, that's it. So is there an element of order greater than 5? The answer is, I guess I should have said that first, but since I'm typing and not handwriting, I can actually just say, yes, there is an element of order greater than 5. Yeah, and it's the primitive element is good, or any primitive element is good. There are actually lots of them, and in fact, actually, that's sort of those are the only elements of order greater than 5, because the orders of elements of the multiplicative group of F16 all divide 15. So the only possible orders are 1, 3, 5, and 15, and so yeah, those are all primitive elements. Okay, so problem 10, good. That was it. Part B, I feel like part B just sort of whipped by there. Excuse me. But I get, which it did. I mean, but that's sort of like either you understand the idea or you don't. It doesn't take a long time to explain it, well, it does not take a long time to explain. It doesn't make it easy, but it doesn't take a long time to explain. So yeah, so if that last bit was mysterious, you should go review the 5 facts for finite fields. This is a good one. Right. So this is, so recall that the parity check matrix of the Hamming 7 code is blah. Yeah, so suppose Yolanda is receiving transmission sent using Hammond semicode, and she receives this vector y here. This vector y, which I guess I should note has ones in coordinates 3, 4, and 6. That'll come in handy later. So correct y to a code word y prime if necessary, and read off the message 3, 5, 6, and 7 to find the intended message m prime. Okay, so to do that, we calculate H7. We're going to calculate the syndrome. You don't need to use this S notation, but I just want to remind you that there is a name for this thing. It's called the syndrome of y is equal to h times y, which is equal to, well, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, oops, 0, 1, 1, 1, 1, 1. Yeah, I got that right. Okay, so that's that times y, which, let me, oops, 0, 0, 1, 1, 0, 1, 0. Okay, and the reason I want to put the ones in a different color is that as I want to point out that entries 3, 4, and 6, because entries 3, 4, and 6 are, so remember, a matrix times a vector is a linear combination of the columns of the matrix corresponding to the coefficients in the vector. And so this is just going to be equal to column 3 of H7, I guess it's H7, plus column 4 of H7 plus column number 6 of H7. Precisely because it's the ones in our vector y show up in entries 3, 4, and 6. So is everybody good with that kind of technique for multiplying? Well, for doing exactly this step of Hamming decoding, which you will have to do on the exam. Like, spoiler alert, you're gonna have to do one of these on the exam, just because the Hamming code is so awesome. I figure, I just love having people do it, and it's a useful thing to learn. So is everybody okay with that technique of matrix vector multiplication? Okay. So in that case, if you add columns 3, 4, and 6 together, we get, let's see, 3, 4, and 6, we get 1, 0, 0. Right, because there's 1, 1 in row 1, 2 ones in row 2, and 2 ones in row 3. And this is the binary digits. And remember the shtick for decoding in the Hamming code is that this is the binary digits of 1. So that means that y prime is going to be equal to y, but with its first digit flipped. And so that's going to be, so we're going to start off with a 1 instead of a 0. And the rest of the digits stay the same. It's 1, 0, 1, 1, 0, 1, 1, 0, 1, 0. Right, so that's what y prime is, and m prime is going to be, you can just read off this. This is, let's see, it says 3, 5, 6, and 7 is 1, 0, 1, 0. And again, we read off digits 3, 5, 6, and 7, which are the agreed upon message bits. Okay, so there we go. That's the name of that tune. So any questions about, are we good on problem number 11? So that's okay. Okay, 2 more. Here we go. Problem 11. So problem 12. Find the GCD of 177 and 78 and solve 177x plus 78y equals d, and show all your work. So let's do it to it. Okay. All right. So 177 is going to be twice 78. I think. Twice 78 is going to be 160 minus 4, which is 156. So 156 plus 21 is 177. Is that right? 14, 156, 77. Okay. And then oops, 78 is about roughly 3 times 21. 3 times 21 plus 3 times 21 is 63. Remainder 15. Here we go. And then 21 is equal to 1 times 15 plus 6. And then 15 is equal to 2 times 6 plus 3. And then 6 is equal to 2 times 3. And that's our last non-zero remainder. So D equals 3. Oh, those are simpler times when we did this, huh? Wow, huh? So everybody good so far? So one interesting thing about this reviewing for the final is now when we sort of look back, you'll see even now we have all these fancy things like groups and whatever. It's interesting to see how much of the course really is still the Euclidean algorithm. So yeah, Euclid. Okay, so let's see. And so I guess just out of, it's useful to call this give this a name, these things names. And so what we have here, so now we're actually gonna have to use signs. Minus is 21. So I'm gonna Euclideanly rewrite. So this is A and this is B. And 21 is equal to A minus 2B. Right, because it says that A is equal to 2B plus 21. And then, and then we keep going. Next, we see that 15 is equal to, oh yeah, this is still B, is equal to B minus 3 times 21 is equal to B minus 3 times A minus 2B, which is equal to, see that minus 3 times minus 2 is 6B, plus 1B is 7B, minus 3A, so that's 15. 6 is equal to 21 minus 15, which is equal to, what was 21? 21 was A minus 2B minus quantity 7B minus 3A, which is equal to, let's see, 4A minus 9B, that's 6. And then 3 is equal to 15 minus 2 times 6, which is equal to 7b minus 3a minus twice 4a minus 9b, which is equal to 7b minus plus 18b is 25b minus 11a. Yipe. Well, there we go. So 177 times minus 11. So this says that x is minus 11 and y is 25, I guess. So this claims that 177 times minus 11 plus 78 times 25 equals 3. Is that really true? Somebody want to check that? I'm going to cheat. Look at this. I'm not above using a calculator. This is like 177 times minus 11. No. Did somebody actually do it? True. Okay. I take your word for it. Let me kill this thing. Okay, so 177 times minus 11 equals 78, plus 78 times 25 is equal to 3. Yay. Whew. Took a little work, but there we go. So good so far. I think we have one more to go. All right. That was problem 12. Let me zoom out so you can see this in its full glory. That's how we get that. That's how we solve that problem. Okay, so one more to go. Oops. What happened there? My renderer is acting up again. Here we go. So I think this is the last one. Yep, that's it. So let I be the set of all polynomials f of x in f13 bracket x such that f of 5 equals 0. In other words, well, so it's the same thing except written out in notation. Prove that I is closed under addition. So what does that mean? Yeah, so really what this is testing, I mean, the very first thing this is testing that you understand if you're going to prove that a set is closed under addition, this is testing to see that you understand what it means for what the assumption and conclusion are for that process. And so what I really recommend that you do is you actually just write out exactly this. You assume that F1 and F2 are in I, and eventually you want to conclude that F1 plus F2 is in I. So, right. So I guess if people run into problems, it is almost always at that stage, right? This is exactly the part that people get where people go astray, and if you don't sort of understand what the assumptions and conclusions are here, then it's really difficult to get this right. You can sort of be around, kind of like nebulously in the neighborhood of the answer, but you're never really going to get the answer. So is everybody good with those assumptions and conclusions? Okay. So what does it mean to say that F1 is in I? Well, to say that F1, so this is this thing over here, that when you plug in 5, you get 0. That's what I have called in the past as the defining condition of I. Right? If that thing is true, then you remember I, and if it isn't, then you're not. So that means, because F1 and F2 are in I, that means that F1 of 5 equals 0. So F1 of 5 equals 0, and F2 of 5 equals 0. And And how is it that how will we reach the conclusion that f1 of x plus f2 of x is in I? We're gonna what needs to happen is that we want f1 of 5 plus f2 of 5 to be equal to 0. Well, I guess we're actually done. Once you sort of write down the answer, then we're done. And once you write down the starting point and the ending point, and you really understand the starting point and the ending point, then we're done. And so that's actually complete proof. So any questions about that? So this is, in some ways, this is entirely set up. Anyway, and if you had a problem, if you ran into problems, and so there's a problem like this on exam 2, no matter sort of what version of exam 2 you took, there's slightly different versions for the makeup, as you may have seen already. Once you get that assumption, that conclusion, usually, I mean, unless I'm in some incredibly bad mood on tomorrow when I write the exam, there should be that's basically, there should be like shouldn't be too hard to bridge what's in the middle, because this is not a proof class per se, and so if I have something with the word proof on it, then it should be relatively straightforward. I mean, what I really want you to understand is that proof is all about, there's assumptions and there's conclusions, and the proof itself is bridging that gap. Okay, so let's do B, and then John V, I remember you had a question. We have a little bit of time for that. So let me go ahead and take a look at, B. Prove that B is closed, that I is closed under multiplication by h of x. And so part B will go like this. Part B says our assumption is that we have some f of x in I, and that we have some random h of x that's not necessarily an I, but it's just some random polynomial. I guess it's just some polynomial in f. Oops. Oh, this should be an 11. My bad. You can tell that it doesn't really matter what the coefficients are, as always, as often as the case. So let h be a random polynomial in f11 bracket x. So a random polynomial with coefficients mod 11. So that's our assumption. And the conclusion we want to reach is that h of x, f of x is in I. So there's our assumption and there's our conclusion. So what does it mean for f of x to be an I? That means that f of 5 equals 0. And there sort of aren't any conditions on h of x. That's actually, this is, I guess, in some ways the more interesting part of the proof, because there are no conditions on h of x. So we can't really do anything with that. What we want, and the goal that we want to reach at the end, is we want that h of 5 times f of 5 is equal to 0, because that's what it means for that polynomial h of x, f of x, to be in I. So is everybody good so far? Yeah, John V, I hope you saved up your question, because you're about to get to ask it in a minute or two. All right, so that's where we're starting. That's where we are ending. And so the important thing now is, is that we just say, oh, well, what do you get when you multiply h of 5 times f of 5? Well, that's equal to h of 5, whatever that is. It's something, whatever. But it doesn't matter what it is, because we're multiplying it by 0. And so we get 0. And so we're done. Okay. So yeah, that one was a little more interesting. There's a little more to that one. All right, so let me pull back and see if we can see the entire answer to the problem. There we go. So any questions? That was the end of the exam. We good? So John B, you had some questions about problem set 11.
Yeah, so there was a question that we have to find a traversal of C2 and C12. So I was able to find C2 and C12, but I didn't understand what was the transversal.
Right. So let me remind you of the definition of transversal. So I'm going to do a similar thing. You know, nobody's been calling my house all day, and all of a sudden, when you guys are here, this is life. Okay, so I'm going to do something. I do not actually remember that problem. And also, you know, I'm sort of a no spoilers kind of guy. But let me do something similar. You know, whoever wrote that song must be so rich. All right. So here's so what I'm going to do here is I'm going to do a problem where we find a transversal for a subgroup H inside a bigger group G. So I'm going to use the one that we did in class because I'm making this up as I go along. So let G be the multiplicative group of the field of order 13, which is the non-zero elements 1, 2, 3, yada yada up through 12, mod 13. Let's see. Hang on. Well, okay. That'll be our gentle music in the background of my explaining this. Okay. Oops. There was a question. So you say the problem in exam 2 with K. Oh yeah. So about the last problem on the final. Yes, the problem in exam 2 with K equals X in R says that rho of X equals 0 is it's not quite identical to this, but it's very, very similar. It's not quite a special case, but it's similar. Yes, I mean, they sort of all look the same. I mean, these essentially all problems are proving that things are ideals. Well, I mean, they don't all look quite the same. The ones in the homework are maybe a little bit different. So one of the ones in the homework is a little bit different. Another one is very similar. This is actually very similar. I don't know. They're sort of both very similar to proving that the null space of a vector space is the null space of a matrix is a subspace of a corresponding vector space. But you know, they're all the same in that. Let me go back to the previous problem since Ryusei is asking this. They're all the same problem in that they all have the important thing to remember. The thing that sort of so the takeaway knowledge from this, the thing that you want to remember, the takeaway knowledge, remember how to set up the assumptions and conclusions for this kind of problem. And I think, you know, it's this is really my fault that I got behind on great looking at your outlines at exactly this point in the semester when we really needed them. So that's my bad. I can't blame the pandemic for all of that. But that's actually why I started having people do outlines, because I wanted because in the outlines you sort of what you do in those outlines, you're supposed to write down exactly this assumption and this conclusion for this kind of a problem. And then if you do that, if you get trained to do that properly, then you sort of start to learn that, well, at least in a sort of first class, there's not much in the middle. It's the important thing to understand is the beginning and the end. Yes. So I'd say Ryusei more largely, all these sorts of closure problems have exactly the same setup in terms of assumption and conclusion. And then sort of what goes in the middle, is really always going to be an application of the defining condition. So that's the structure that you want to sort of see in common among all these problems. So Ryusei, does that make sense? Yes. Assumptions and conclusions. All right. Okay. Let me get back to John B's question. All right, so we're doing a problem where we find a transversal for some subgroup H inside a bigger group G, and let me see. I hope. Oh yeah, actually I know this is gonna work. Let H. Let H be the subgroup of G generated by 4, which is the powers of 4. If there's 4 to the 0, 4 to the 1, 4 squared is 16 mod 13 is 3. 4 cubed, which is 3 times 4 is 12. And then oops, do I want to do this? 4 to the 4th. I think I might have to go back and change this. 4 to the 4th is 48. Oh, okay, which is something. Okay, so I was this made more sense. This made more sense for 16. So let me instead do 8. Yeah, let me do 8. Sorry, I'm going to change this. All right, as I was saying before, I so rudely interrupted myself. Let H be the cyclic subgroup generated by 8, which is the powers of 8, which is 1, 8, 64 mod 13. 32 is 0 mod 13, so this is 12. 52, 64, okay, great. 12 by 8 is 96. Mod 13 is 5, and 5 times 8 is 40, which is mod 13 is 1. Okay, so I just did that a little bit quickly, but you can just pretend that you have some mod 13 computer, and that's the way that works. Okay, so this is the cyclic subgroup generated by 8. Okay, so there's yeah, this is 8. So just in case, I mean, I'm doing this quickly because we are somewhat limited on time, but this is 8 squared, and this is 8 cubed mod 13, as it happens. And you can just do this on your calculator, or you won't have to do something like this on the test, but you'd imagine as I hope you've seen, the amount of calculation you have to do in an exam is minimal because you're not allowed to have a calculator. But let's just pretend that I did that out. So there's your subgroup H, and now right, we want to find a transversal for H inside G. That was John B's original question. Sorry, it took me a little while to generate an example there. So to find a transversal for H in G, you list all of the cosets of H in G, and pick one representative each coset. All right, so so the point is we're gonna do this by somehow listing all the cosets of H and G, and picking one representative from each coset. So how do we do that? What we do is that as we do this, is we want to start choosing. Well, let's find something that's not an H. So let's see. 1 is an H. Okay, that's done. So 2 is not an H. 2 is not in H. So what we do next is we find 2H equals, and to calculate 2H, the coset 2H, I'm just going to multiply, take all the things in H and multiply them by 2. 1 times 2 is 2. 8 times 2 is 16, which is 3 mod 13. 12 times 2 is 24, which is 11 mod 13. And 2 times 5 is 10, which is 10 mod 13. So this is 2, 3, 10, 11. So what else have we not hit? 1, 2, 3, 4. I guess 4 is not an H. And so let's do that next. 4H is equal to 4. Let's see. 1 times 4 is 4. 8 times 4 is 32, which is 6 mod 13. 12 times 4 is 48, which is 9 mod 13, and 5 times 4 is 20, which is 7 mod 13. Again, I just kind of did that quick in my head, but because I've been doing this for a long time. But you can imagine sort of doing this a little more painstakingly, or with a calculator or something. And did we get everybody? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, we now have every element of G. And so we see that G is equal to the disjoint union of H and 2H and 4H. I guess H is, you can think of it as 1H. And none of those sets have any overlap, as we just saw. And so, 1, 2, 4 is a transversal for H in G. Wow, that was like a super long answer to your question. So, but does that make sense?
Yes, this makes sense. Thank you, Professor.
Okay, you're welcome. Kosha, you're asking, do we need to do the revisions? Are we fine without them? Let's see. So, do you need to do the revisions? Well, it's never a requirement to do the revisions. So I think the thing to do is, well, you may have noticed that we never quite finish anything. We just run out of time. And so the same thing will happen with the course. Your order of priority should be, you should try to finish all the problem sets first. Besides studying for the final, which is of course very important between now and Friday, 1, finish as many problem sets as you can first before sort of time runs out of the semester, and then 2, if you have extra time, then you can revise anything that I've graded. Go back and revise any problem set that I've graded. So if you're supposed to, how we submit them, as there isn't a code for the points earned. You should have. I am now grading the problem sets through Gradescope, so you should see how many points you're sort of receiving or missing on every problem, and then you can revise them accordingly. So let me just write out the answer to Kaushal's question. Question. Actually, I think I can type this in. I can and should type this in. How do we know what to revise on various problem sets that have been graded? Answer. So answer 1 is the first priority is to finish all of the problem sets the first time. Then you can do revisions of anything I have graded. Just submit them on Canvas, and I'll figure it out. So because what happens is I actually have I have the equivalent of that number code stored on Gradescope, and so I will figure it out somehow. Just submit it on Canvas in the revisions bin, and I'll figure it out. It's a little chaotic. You can sort of see on, like, as we've gone online, I've started switching systems, like trying out different systems one by one. And I think, in the fall, I'm going to do everything through Gradescope. I mean, I don't know if you've noticed, but I think Gradescope is awesome. You may or may not share my opinion, but it's super convenient for professors. and I think it's not. I hope it's not bad for. I mean, especially once I sort of get better at using it, it'll be useful for students. And certainly we had something like that is necessary for online. So anyway, so whatever. But this semester things are a little chaotic because we're I said at the beginning of the semester we're going to be building the plane as we fly it, but I didn't realize how much we're going to be building the plane as we're flying it. So we're building every aspect of the course as we're flying it, but hopefully, just a couple more days, we're gonna make it, friends. All right, so it's 4:49. Time for one more question. I think it's probably too late to start doing answers for exam 2. Should we give up then? I'm a little tired now. You guys must be a little bit bored for listening for me 2 hours. So should we give? So whoops.
Professor.
Yeah, go ahead.
So is May 19th, 11:59 p.m. the absolute deadline for everything?
Is that the absolute deadline? That is a stated deadline, but all that deadline's flexible too. Okay. Let me know if you need some more time.
Okay, thank you.
All right, so I'm reluctant to type that in, but okay, yeah. Let me know if you need some more time. Should we give up now then? Okay, let's give up. Thank you very much for being here. Goodbye, YouTube, and I will stop recording and stop sharing now. It's been an honor and a pleasure again to hang out with you. See you on Friday.